Now we'll talk about statistical significance. Statistical significance occurs when the observed difference or relationship is too large to be explained by chance alone. Statistical significance plays a pivotal role in statistical hypothesis testing, where it is used to determine whether a null hypothesis should be rejected or retained. A null hypothesis is the general or default statement that nothing happened or changed. For a null hypothesis to be rejected as false, the result has to be identified as being statistically significant, or another way of saying that would be it is unlikely to have occurred due to sampling error alone. To determine whether a result is statistically significant, a researcher would have to calculate a p-value, which is the probability of observing an effect given that the null hypothesis is true. The null hypothesis is rejected if the p-value is less than the significance, or alpha level. The alpha level is the probability of rejecting the null hypothesis, given that it is true, and it is most often set at 0.05, or 5%. So in this case, a statistically significant result is one that the observed p-value is less than 5%, which is formally written as p less than 0.05. For more detailed information about the value 0.05, you can read Jane's Superbrain 2.5 on page 78 of the field textbook. Keep in mind that a result may be statistically significant, but that doesn't mean that it's necessarily clinically significant. Clinical significance is the practical importance of a treatment effect, whether it has a real, genuine, noticeable effect on daily life. This can be calculated using effect size, number needed to treat, or NTT, or other methods. If the p-value is less than or equal to the chosen significance level, or alpha, the test suggests that the observed data are inconsistent with the null hypothesis, so the null hypothesis must be rejected. However, that does not prove that the tested hypothesis is true. When the p-value is calculated correctly, this test guarantees that a type 1 error rate is at most the alpha level. For a typical analysis, a widely used interpretation is a small p-value, a p-value of less than or equal to 0.05, indicates strong evidence against the null hypothesis, so it is rejected. A large p-value, greater than 0.05, indicates weak evidence against the null hypothesis, so you fail to reject it. P-values that are very close to the cutoff of 0.05 are considered to be marginal. They need more attention or more samples to be studied to draw a better conclusion. The analysis must always report the p-value so that readers can draw their own conclusions. In this course, please report the exact p-value to 3 decimal places as it is found in the SPSS output window. Effect size is the measure of the size of experimental manipulations, or the strength of a relationship between variables or groups. Effect sizes can be compared across different studies that have measured different variables or different scales of measurement. Effect size helps readers understand the magnitude of differences found, whereas statistical significance examines whether the findings are likely to be due to chance. Both these values are essential for readers to understand the full impact of research, and should be reported in both the abstract and results of journal articles. Effect size can be measured with Cohen's d, the partial eta squared, a Pearson's correlation, which we'll cover in Module 10, odds ratio, and relative risk. Cohen's d is the difference between two means, divided by the standardized mean difference. The standardized mean difference simply means that you can compare the effect sizes across different studies that use different dependent variables. It is interpreted as a d-value of 0.2 is small, 0.5 is medium, and 0.8 is large. Note that the value of Cohen's d can be greater than 1 or 2, but this would reflect that the two means are larger than 1 or 2 standard deviations away from each other, which is really rare. An example of Cohen's d is two studies that are measuring the mean difference in two different dependent variables between an exercise treatment group and a control group. In the first study, the dependent variable is average heart rate per minute, and in the second study, the dependent variable is ventricle size. So after they run their tests, an effect size could be calculated for each study, and then that could be compared to see if both studies experienced a small, medium, or large effect between the exercise treatment group and the control group. The partial eta squared measures the proportion of total variability in the dependent variable that can be attributed to an independent variable, as well as the mean difference in a dependent variable between independent variable groups. For example, the mean BMI was found to be statistically different between an exercise treatment group and a control group, with the p-value of less than 0.05. The computed effect size helps determine clinical significance. A partial eta squared of 0.75 for the main effect program would be considered a large effect, which means there's a large average difference in the dependent variable between the exercise treatment group and the control group, or 75% of the dependent variable was accounted for by the program. A partial eta squared of 0.15 would be considered a small effect, or a small average difference. But the question is if the difference is it clinically meaningful? So is it clinically meaningful to require patients to participate in the exercise treatment or not?